for that. Alrighty, so can you all see my purple slides? Yeah, I'm pointing to my other monitor as if that helps you. Yes. All right, let me get the chat window open, make sure I don't miss anything. So I'm trying my darndest to do the divided attention of remembering what the words are coming out of my mouth while monitoring your faces while monitoring the chat window. So if you have a question and I appear to not be noticing, please feel free to stop me because this is not meant to be a lecture, it's meant to be a conversation. So please feel free to jump in at any time. Just think of me as the friend that doesn't always realize when it's not her turn to talk anymore. And you have to be like a little bit more like, okay, I'm going to switch topics now to peel their attention away. Just think of me like that friend who might need a little extra prodding to realize when it's not their turn. So, but please do keep the questions coming. I like it. It's fun. All right, so before we dive back into stuff, any logistics questions? Anything that we need to chat about that's more general? No, we're good. Okay. All right then. So we were talking about dimensionality and ways of exploring dimensionality. So heading back to sort of the big picture in thinking about how do you know if an instrument is doing what you want it to be doing? Scroll, 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 scroll back. Big picture here. Validity, reliability, dimensionality. So in my view, these are the big concerns that we have to worry about in scale development. Validity, whether or not we're measuring the right thing. That is pretty much impossible to say with any sort of definitive yes, because it always depends on the situation in which you're using it and the purpose that you're using a measure. But before we can try to get to the point where we show evidence of validity, we have to demonstrate reliability because you have to measure something before you can understand whether or not it's the right something. And all indices of reliability, or at least the vast majority, presuppose a known dimensionality. Most of them are meant for unidimensional traits, where each trait that you're measuring has its own index or indices of reliability. So what we're talking about here are old school ways of assessing dimensionality. Exploratory methods being the big difference. As you may have picked up on my not so subtle comments, I'm not a fan. I am not a fan of exploratory analyses. So I am equally not a fan in the context of continuous latent traits, so the world of exploratory factor analysis and principal component analysis as a related technique that we're talking about. But the same problems hold with things like latent class analysis or latent profile analysis, which is for traits that are considered categorical or attributes. You can fit a model to try and find how many hidden classes, um, how many different hidden classes of growth trajectories in a growth mixture models. And someone could say, well, I think there's 2 classes and here's what it says, and I think there's 3 and here's what it says, and you're both right. And that's the problem. So I wanted to present these techniques with just enough detail for you to understand how what we're going to do is necessarily different and, in my opinion, more useful as a result. So old school dimensionality is what we're talking about. We talked about stuff. Let me get to the slide where we were because this is really the crux of the argument as to the difference between these things. So picking up on 14. What's the difference between these different methods that are similar but not doing the same thing? That difference aligns itself directly to the distinction between formative indicators and reflective indicators. So PCA, principal component analysis. The point of PCA is to summarize or abbreviate a larger series of observed variables. So when you have a whole bunch of data and you don't want to keep all the individual variables, you just want to summarize the information in them in some more succinct way to then take into a subsequent analysis. That is what PCA is for. It works for things like measures of electrodes or fMRI measures or things where you just have a shit ton of data and you can't work with all of it and you want to find some way to abbreviate it. And so you have as many components that you can extract as you have indicators, but you would never want to extract all of them because that would just create as the same problem. You'd just have components instead of indicators. So you want to extract as many as it takes to represent enough variance. How many? Meh. There's not a hard and fast rule. There's guidelines, but they're not always that useful. So the idea of component analysis is that the component is then an outcome. What the model gives you are weights that are applied to the indicators or to the items. So remember, indicator is the same thing as item is the same thing as observed measure. So the things that you actually have in your data set that you've collected. They get weighted and combined in a linear fashion to create this composite. So the composite to be created is an outcome of the combination of these indicators. So that aligns itself with a formative model. And we talked about this a little bit. I put up a new article, but some classic examples of formative measurement models, socioeconomic status. If you somehow have your education and your zip code and your parents' education and how much money you make, and you just lump all that together in some way, that creates this new outcome that is socioeconomic status. That in turn can be measured by, that can predict other things. Another example that I really like that came from the articles, either the article I gave you or one of the other ones that I read and decided not to include, was home value. So we can think of home value as either a formative, we can think of formative indicators of home value, but we could also think of reflective indicators of home value. So if I want to know how much my house is worth, how do I get that information? Are any of you homeowners yet by chance? See, the correct answer should be no, because the American dream is not owning a home anymore. The American dream is being out of debt. So good for you for renting, because that's a very good, sound economic decision. When I bought my very first house, when I had my very first job, I ended up taking out 3 different loans to afford it. Spoiler alert, if you need 3 loans to afford a mortgage, you probably are overextended. So, but at any rate, no matter how much money you do or you don't have, any home has some kind of value, and that value is not always the same, right? It depends on a lot of things. So if I want to figure out how much my home is worth, I could ask a real estate agent to come over, and they would generate other houses that are similar that have sold recently, and they'd come up with some sort of price based off of those. I could get an appraiser. So if you renegotiate your mortgage, you usually have to get an appraisal as part of that process. When you sign up for an initial mortgage, you also have to get an appraisal. And so that's someone whose job it is to come to your house and try to figure out how much it's worth. So let's say that I asked a couple different real estate agents, I got a couple different appraisals, and they each gave me a number. And that would be creating a latent factor of home value. Now that is a situation in which those would be reflective indicators, right? My home has some value. I don't know what it is, but I'm asking all these people what they think it is. And hopefully they can sort of triangulate on some kind of agreement. And so in that case, with reflective, you would expect that if these assessors are doing their job correctly, they should agree, right? There should be some correlation there, hopefully. If not, then we have a big problem. So in exploratory factor analysis, what you're trying to do is to figure out how many latent factors are responsible for the observed pattern of correlation between the indicators. So in EFA, you're working with just the common variance between the indicators and trying to assign that to factors. So EFA is conceptually backwards from PCA. PCA, the component that you're creating is the outcome. Continuing the home value analogy, what makes a house valuable? So I'm seeing the question here and I'm going to get to it, I promise. What makes a house valuable? What makes a house cost more than other houses? Well, how much square footage? How many bathrooms? How many bedrooms? If it's on the water, yes, waterfront property in Iowa, not a thing. Whether it has a pool, that could potentially add value, although actually it ends up subtracting value a lot of times because not a lot of people want a pool. But there's a number of factors that sort of come together to create a home that has value. And they may be related, right? Like the more square footage you have, the more room you have to carve out an extra bedroom or an extra bathroom. But even of homes of comparable square footage, if you find a way to add an extra bedroom, that adds value. So you can think of aspects of the home, lot size, square footage, number of bedrooms, number of bathrooms, the neighborhood that it's in, the school district that it's in, all that kind of stuff. How far away it is from a flood zone, that's something relevant. That's something we considered in looking at our house when we were shopping. All of those things come together to create this latent construct that is home value. They're formative. They may be related, but they don't necessarily have to be. So home value is an outcome of things like square footage, number of bathrooms, number of bedrooms, and so forth. But to get at what that home's value is, we could ask people what they think it is, and that part would be reflective. So it turns out that the only way that you can actually test a formative measurement model is if you have both. You have to have both the formative indicators and the stuff that's it's supposed to be related to before it becomes mathematically solvable. So questions from the audience here. Why is any correlation between the indicators essentially irrelevant? Because in principal component analysis, it's not trying to reproduce the correlation. It's trying to reproduce the variance. It's trying to summarize the set of variables. And so it's not the same objective, and it's an outcome as a component, whereas the EFA, the factor, is a predictor. So we have, I think the next one, yeah, pictures next and then equations. So the big difference is the direction of the arrows. So the formative model that corresponds to a component analysis is on the left. And in these pictures, you're going to see a whole lot of them this semester. They all follow the same conventions. Any item that is in a box is real. So they are observed variables. So this would be an instance in which we have 4 outcomes, 4 variables that exist in our data set. Any item that is in a circle or an oval is not real. It's something that it's a variable whose variance is estimated by the model, and we don't know what it is ahead of time. So on the left here is a component model where the observed variables have potentially correlations between them or not. It kind of doesn't matter. This set of arrows right here with a line connecting them, that is a cheaty way to show all possible correlations. Correlations in these types of pictures are shown with arrows that have 2 sides to them, so a 2-headed arrow. And rather than showing all 6 arrows that you would have among these 4 variables, I did a shorthand, which is just to show that they're all sort of connected here. So that's what this notation is meant. But the big picture, the big thing that's important is the arrows coming out of the boxes into the circle. So this would be like square footage, lot size, number of bedrooms, number of bathrooms, right? They combine to create this new latent construct that is home value. And there's no way to know if these indicators have been combined correctly, because home value doesn't exist. This is not like a regression model where I've got 4 x's and 1 y, and I can tell how much of the y variance the x's have accounted for. I don't have a y. It's not here. It's latent. The same is true on the right-hand side, that I don't have something, but the something I don't have is an X. The arrows come out of the circle into the indicators. This is a reflective model that's consistent with EFA. So question, having trouble connecting this to the causal indicators paper. Causal indicators and formative, I would lump into the same category. The paper that I sent you made a distinction between indicators that are just added together to create something and indicators that are thought to be conceptually similar, but in practice, you don't know which kind you have. So to me, that distinction is more theoretical than useful. But the big distinction that I want to keep a hold of is just which way the arrows go in this idea. Is the trait something that you have and it causes the way you answer the questions? Because if that is true, then your answers to the question should be correlated. So another way of saying this is that the existence of this factor is predicated on there being correlations. Its job is actually to predict, to anticipate what those correlations are. And after you control for the factor, the observed indicators are supposed to be unrelated to each other. That's what's known as local independence. Do we always want formatives and reflective indicators? The model on the right that only has reflective indicators is identified, meaning it is mathematically solvable. I could figure out what numbers correspond to each of my arrows. The model on the left is not identified because all I have are the correlations among these indicators. I don't have enough information left over to figure out how they should combine to create this new thing. The only way that this component model would be identified is if I also had reflective indicators. So I'd have to have arrows coming from the component to other stuff, which then introduces more correlations into the matrix for these paths to all be solvable, for the model to be identified. And so you can think of it as either having the component model also needs reflective indicators to be identified, or it needs just other outcomes that are related to it. And that turns out to be somewhat of a semantic distinction because statistically they're the same thing. But it needs some other variables that it in turn predicts for the model to be solvable, to be identified. So other question, when we assess model fit for a reflective model, we're assessing how well the factor accounts for those intercorrelations, right? Exactly right. So how we know whether or not, say, these 4 items on the right are part of one factor or 2 factors boils down to their pattern of correlation. In the factor models that we're going to talk about this semester, and this is a picture that aligns itself with CFA, but the same is true in IRT and IFA models and any kind of latent trait model. The pattern of correlation between the indicators is the evidence for the dimensionality. And you can specify one trait saying, if one trait is causing these, then the pattern should look like this. And you compare that predicted pattern to the actual pattern and you see how close they match. How close they match is absolute model fit. You can then specify an alternative model, say, that has 2 factors in it. Say, no, I think that 1 and 2 measure this and 3 and 4 measure that. And so long as the 2 factors are related, that's identified, and you can compare the fit of that model against the model that says, no, they all measure the same thing. Because each of those models in turn implies a different correlation pattern that can be compared to the observed data. On the left, you have the correlations separately. The component does not cause, imply, or predict the correlations between the indicators. It's separate. It's not identified. So we need extra stuff in there to be able to figure out what the weights should be for the loadings that create this component And it's even harder to figure out then how much of the component would be left over, what the error variance would be. That parameter is especially hard to identify. So PCA is the left side, where the component is an outcome and the observed variables are the predictors. In component analysis, we assume that the outcome is linearly predicted by the indicators. There's no error term that is relevant. In factor analysis, on the right-hand side, the factor is the predictor. It's latent. We don't have it, but that's not going to stop us. And the factor is the reason for the correlations between the indicators. So putting that in equations, it looks like this. And so I had 5 on here rather than 4. Someone pointed out after class, I forget who it was, but thank you for that comment, that I'm switching back and forth across between 5 and 4 indicators. That's just me being inconsistent in what I had room to show. But the big difference is whether or not the trait that we're talking about is an outcome versus a predictor. In component analysis, the component is what the trait is called. It's an outcome. In factor analysis, the factor is the predictor, the trait that we're talking about, and the indicator is the outcome. And so then this starts to look a lot more like a regular regression model, where you're saying that your indicator, the response that you gave, is a function of your standing on the first trait, your standing on the second trait, and then there's probably some variability that's unaccounted for in your response, and that's E. Okay. Am I frozen? No? Okay, we're still together? All right, I feel like we're drifting apart here. Zoom. There we go. We're back. So the reason that I don't like this actually is on this one slide. What if I had an a priori hypothesis that items 1 and 2 measured F1 and items 3, 4, and 5 measured F2? Could I do that? Sure. Can I test it with EFA? No. I can tell it, give me one factor, and it'll give me a set of loadings for that one factor. I could say, give me 2 factors, and it'll give me a set of loadings for everything. In EFA, every item loads on every factor. Every factor is supposed to predict every item to some extent. That's what it does. Even if you don't think that that's true, that's what you're stuck with. And it turns out that this system of equations is not solvable unless you put some kind of mathematical constraint on it, and the constraint that gets used in EFA makes no sense. It's coming. But the constraints that we use in CFA are designed to specify theoretically what the factor is. So the constraints that we would use in CFA is, okay, well, if I think that items 1 and 2 are only measuring factor 1, I would take these loadings for factor 2 and force them to be 0. And I would do the same thing for the loadings of F1 for items 1, 2, or 3, 4, and 5. I would force those loadings to be 0. And that's a constraint that mathematically identifies the model and also represents my theory as to what I think is going on. And I can see how well the data match the implied model. So yeah, here's the constraint. I actually had to write it down because it's so convoluted I didn't trust myself to actually say it. So if I have 2 factors, the constraint that people put on in the EFA to make it identified is that the sum across items of all loadings times the item's error variances must be 0. Yeah, that face. T, you're making a great face. That's exactly right. Like, what? Yes. Yeah, that is the constraint that's used to make the EFA identified. It's not helpful. There are more helpful ways to do it. So even if you think that you have an idea that only some items should measure some factors, there's nothing you can do about it. You're stuck with this everything is measuring everything philosophy. So you can test alternative models and compare how well they fit within a confirmatory framework. We're going to use confirmatory factor analysis in a more exploratory way, in the sense that we may compare different models and see how they fit. The key is gathering some set of evidence that everyone would look at it and say, yes, two factors fits better than one, or nope, you don't need two factors, there's only one there, where there's a more definitive answer to that question as to how many factors are being measured. So after you're deciding how to go about getting these loadings, the second step is to determine how many factors you have. In these exploratory procedures, you can tell it, give me one, give me two, give me three, and it'll happily do that. But that's theoretically what you're supposed to be measuring. That's the question that's being answered, is how many traits are being measured and what are they? It is not your computer's job to figure that out. It's just not. Computers aren't good at it. A lot of the rules about how many factors or components that you should keep. So how many factors are responsible for the observed pattern of correlation in EFA, or alternatively, how many components are enough to summarize the observed variables variances. It's the same type of question in each case, are based on eigenvalues. And this is how much of the total variance is being accounted for by the factor or by the component, even though what total means is different between these two. And there's three rules that people use. Eigenvalues over 1, and then staring at pictures are the second and third. So you may have heard this before if you've seen PCA and EFA, that any eigenvalue over 1 is thought to be keepable with respect to your components or the number of factors. This actually only makes sense for component analysis, because what 1 means in the context of component analysis is that the component captured as much information as at least one variable's worth, because we're dealing with the correlation matrix in which all the variances have been standardized to 1. So a component with an eigenvalue of 1 means it got at least one variable's worth of information. That's a pretty low bar, right? Because we wanted to summarize a bunch of variables. Just getting one variable's worth is a low bar. That's not probably helpful. Even though it doesn't make sense, people use this rule in EFA, where the diagonal of the correlation matrix is not 1, but it's the communality, the amount of common variance. And so 1 doesn't make sense, but this tends not to work very well. You tend to keep too much stuff. The other rule that people use is not a rule, it's stare at a picture. What's known as a scree plot. You seen these before? You're supposed to look at a picture like this and say, you know where it bends? Right before that, that's how many components or factors you need. So this picture arguably shows that 1 for sure, but then you get into like, is the bend at 2 or is it at 4? So an alternative to just going meh is to simulate random data and use that. That's what's known as a parallel plot. I have no idea if this is still being used because I don't ever recommend EFA, but in that case, you would compare where your line falls against random data and pick the components that are above random. So once you've decided on the number of factors, then comes rotation. And this is the process of trying to make your factors useful, which the computer is again going to do for you. So here's where the bigger problem comes in, is that rotations are different ways of looking at the same solution. They are each equally correct as the next. They fall in two different main families, orthogonal versus oblique. Do I have that on this slide? Yeah, that's coming. Orthogonal means uncorrelated. So if you think of this type of pattern, did anyone watch, what was the show, Trading Spaces? I'm dating myself. But this was like early like HGTV. This was actually on the Learning Channel, like before all the home renovation shows like became a thing. There was this show called Trading Spaces where neighbors would trade and each would like redecorate one of the rooms in each other's houses over a weekend. It was entertaining. I'm not sure why, but I liked it back in the day. And I remember one episode where there was this designer, her name was Hildy, and she was known for doing very extreme things. And she kept insisting that the concept for the episode was going to be orthogonal design. Orthogonal design. And she just kept saying this word, and the homemakers are like, what? No, she meant plaid. That's what she meant. She had like this blue and white like set of lines on a basement that it worked out to be plaid. That's what orthogonal design meant. But I always think of her when I hear the word orthogonal. It just means uncorrelated, meaning that you can twist the solution around any way you want so long as the factors stay uncorrelated. And in oblique, they get to have a correlation. Now, arguably, oblique is more appropriate for most real-world contexts with multiple factors because usually what you have are factors that are going to be related to each other because they're part of one common instrument. Like you have, the emotional dysregulation scales where you have, different ways of being emotionally dysregulated or different types of anxiety or different, sub areas of some construct. People will throw all of those into a factor analysis and you would expect them to be related to some point. So oblique rotation would be more useful in practice in most cases. So it looks like this. So let's say that we have a component solution here. This is from a couple slides ago where here's the loadings on C1 and here's the loadings on C2, and what do I do with that? Well, you can take that original solution and you can rotate the axes. So literally take your grid here and go like that. Okay. I think, wait, it's backwards for you guys. It needs to go this way, doesn't it? Is that better? Okay, I am never going to get that right. I am never going to be able to do that, but I'm going to keep trying. I promise that. So in the new solution, it looks a little bit easier to eyeball these numbers and go, okay, it sort of looks like component 1 is summarizing items 1 and 2, whereas component 2 is sort of summarizing not 3 and 4. Like whatever the opposite of 3 and 4 is, that's what component 2 measures. And I'm just making this shit up because I can get this solution, I can get another rotated solution and be like, now it looks like it's 1 and 4 and 2 and 3, and I could still be equally right. An oblique solution would do the same thing, but relax the angle so that the factors get to be correlated. And there's like 18 kinds of these. Here's types of orthogonal rotations that you would have heard about. By the way, did anyone else here grow up in undergrad on SPSS? Remember that software package? Kayla, represent, yes. Anyone else? Andrea, yeah. Lots of people, okay. Yes, so me too. I learned how to use SPSS. I learned how to use it actually before there was Windows SPSS. That's how old I am. Yes. SPSS did not always have a GUI. You used to just have to type code in it. But anyway, if you go down to SPSS in the Windows and there's a command to do what it calls factor analysis, do you know what the default is if you don't make any other choices under factor analysis? It's principal components, not factor analysis, with a Varimax rotation. Do you know how many papers have been published by social science people thinking they did an EFA where they actually did a PCA with Varimax rotation? A lot. A lot. And I think it's SPSS's fault because that's the default. If you are used to using Windows and you leave all the other choices as they are, that's what you get. So Varimax is the default. So these are kinds of orthogonal rotations. These are kinds of oblique rotations. So now you have not just ambiguity as to how many factors or components is enough, and again, they're doing different things. How many factors is enough to reproduce the observed pattern of correlation among the indicators, or how many components is enough to capture enough information in the indicators. But then you also have within each type of solution, 2 factors, 3 factors, 4 factors, whatever, what kind of rotation you need. And so you will see papers published in good journals that are like EFA wars, where, group number 1 is like, I factor analyze this scale and I think it's 3 factors and I think it's Promax. And then 2 years later, group B is like, nuh-uh, it's 4 factors in direct Ableman. And you know what? Guess who's right? Exactly. They both are. They both are. And it's silly. And that's why I don't want you to do this, because everybody's right, and that's not helpful to you. So if you have a hypothesis at all about what is being measured, that's enough to get started. And even if you don't, you can recreate an EFA solution inside a CFA model, but you get significance tests for the loadings. That can help you trim down which ones are not actually measuring which constructs. And if you put a model together that says, okay, these items are measuring this trait and these items are measuring this trait, and it fits badly, you get diagnostic information as to where you're wrong. It's like, oh, no, 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 no. These two items are much more related than the model says, so they're probably measuring the same thing. We need to move them onto the same factor. Now, that's all exploratory, right? Like that's messing about with your model as a function of data. And so all of the concerns about messing with your model as a function of data apply. You would want to have another sample with which to hopefully get the same model to fit again to have some sort of faith in it. But point being, exploratory type analyses conducted in a framework where you can say, yes, this is right or no, this is wrong are going to help you. So don't get into the like, well, how many factors is it and what's the rotation that fits best, because there is no best. There's just not. So it's not helpful. Interpreting the solution, you pick some arbitrary threshold for how much a loading needs to be, like 0.3, 0.4. And if it meets that threshold, you say it loads on the factor, which means it is measuring that factor. And if it's under 0.3 or 0.4, you say it's not. Again, no standard errors, no significance tests, none of that as a standard byproduct. People have figured out how to get them. Like if you run an exploratory factor analysis in M+ using maximum likelihood, you get standard errors and you could probably get p-values if you ask it to. But it's still the same problem that all items are theoretically measuring everything. And so you don't really know what their factors are. There's no hard and fast way to talk about what you've actually got. There's more sets of factor loadings to contend with in oblique solutions. You can end up with loadings that reflect the bivariate correlation of the indicator with the factor or the partial correlation of the indicator with the factor. So then you can fight about which set of those you should be interpreting. So that's yet a third dimension of ambiguity. Yep. And then there's this. There's lots of reasons why indicators could be correlated, and some of those reasons may have nothing to do with what they measure. So if you had say, a dyadic design where you asked somebody to rate various attributes about themselves, and then you asked their partner to rate various attributes about the person, the responses from the partner are probably going to be more related, and the responses from the self are going to be more related, regardless of what the characteristic is that you're asking them about. Items that are negatively worded, where you have to say, I am not unhappy, and then versus I am happy. Those are going to be related. EFA offers you no way of saying, well, the reason that I have this trait is because of this common way of measuring it, and the reason that I have this trait is because of the thing that's being measured. There's none of those fine-tuned distinctions that are applicable. So it's very unsatisfying, ultimately, in testing why you think things are the way that they are. So yeah, have I convinced you yet? By the way, are you convincing that those of you who haven't studied this before, you're not missing out on anything? Are some of the differences between the rotation methods used in PCA or EFA? To some extent, I think PCA has more of a tendency to favor orthogonal rotations, whereas EFA tends to be used in the context of scales where you would have subscales that should be related, and so oblique rotations lend themselves to that a little bit more. But there's no way to say which rotation is the rightest for any one situation. That's the big problem that I have. Factor scores, you can ask for factor scores, don't. They're indeterminate. There's a whole bunch of different ways that are mathematically equally valid to get sets of factor scores that have very little to do with each other. So we don't want factor scores. It turns out that the whole motivation for this class, structural equation models, is to avoid having to get factor scores. Let me go back to my picture here. Way back. Let's go back way back to a factor model. There we go. This picture right here on the right. This is my nice little baby measurement model. If I want to figure out how factor predicts some other outcome, I would put the outcome in the model as another box, draw an arrow from factor to that other box, and estimate that regression. I don't need to have actual scores for people that become an observed variable to answer questions about how that latent variable relates to other stuff. It can stay latent. And the other stuff can stay latent too. You don't actually need the scores. That's the motivation for structural equation models, is just to keep things latent. That way you don't inadvertently assume things about your scores that you shouldn't, like they're perfectly reliable, rather than differentially unreliable, as the case may be. We will talk a little bit about factor scores in this class because I want you to recognize their limitations. There are always limitations. The only question is how bad, and that depends on the quality of measurement. Generally speaking, the more indicators that you have, the more they're related to the trait, the more you can trust your factor scores, so to speak. All right. I think that was where we were. Yeah, that's it. Okay, so I realize that that's a relatively quick overview, but that's because I didn't want to spend a whole lot of time on it. But are there questions from you that I haven't hit yet? I've been trying to keep an eye on the chat window. Okay, so big picture, the problem with exploratory methods is that there's no way to say which final solution is more right than another. And even if you switch to EFA using maximum likelihood, in which you do get some sort of model fit, there's no way to say what the hell your factors mean in the first place because everything is thought to measure everything else. So it's dissatisfying from that perspective, even in a maximum likelihood framework. So we will use models instead that are confirmatory in nature, where the only difference between frozen, okay, it's back, or back close enough anyway. The only difference between the models that we'll talk about, which are all confirmatory, is in what kind of relationship we need to be able to describe how the trait predicts the observed variables. Some of them will be linear relationships and some of them will be nonlinear and corresponding with different types of outcome variables. That's going to be the big difference. All right. So thoughts, questions before we change gears? Okay, the next thing I want to do is disabuse you of the notion of alpha being useful. That's lecture 3.